All right. In chapter 4, we're going to be looking at functions. We're looking at single variables for a very long time, x equals, x equals, x equals. We're going to be looking at functions that involve more than one variable. We're going to start with just looking at some different graphs. Very little arithmetic in this. We're just looking at graphs and how do they relate to each other. So, graphs can be used to illustrate lots of different things. It's a great visual, gives us a general overarching idea. It's not a great tool for very specific things, but it's a really nice visual and general description of what's going on. Example, each day several leaves fall from a tree. One day a gust of wind blows off many leaves. Eventually there are no more leaves on the tree. Choose the graph that best represents this situation. And so you have to look at these three graphs, graph A, graph B, graph C, and decide which one do you think matches best. So take a second. You got a 33% chance of getting this right. Look at the situation, see if you can figure out which one matches. I'm going to assume you did that. If you look at graph A, as time goes on, and again we're going to be looking at that at those labels, the number of leaves in graph A go up. So as time goes on, the tree is gaining leaves, and that does not happen in this situation. So it's definitely not graph A. For graph B, it's losing leaves, so that's good. Graph C, also losing leaves right away. So it says one day the gust of wind blows off a lot of leaves, and eventually there are no more leaves on the tree. If we look at graph C, there's a time period when it's very stagnant, where it stays the same. And so this says that each day several leaves fall from a tree. Then there's lots of leaves that are being blown off, and eventually there's just no more leaves. And if you look at graph B, that's the one that matches the situation. So the answer is graph B. Let's look at another example. I'll let you read it. Take a guess, and we'll do it together. I'm going to assume that you read it, that you paused it, you tried it on your own. So as the temperature, as time goes on, the temperature is changing. So the air temperature increases steadily for several hours. If it's increasing steadily, that's not increasing. That's pretty much flat. That's not increasing. That's pretty much flat. That's steadily increasing. Let's make sure that it works for the rest of it, though, but I think C might be our answer. At the end of the day, the air temperature increases slightly before dropping sharply. So at the end of the day, it goes up sharply and then drops off sharply. Okay, there we go. There's our answer, graph C. Now, there are different types of situations. Some are continuous, and some are what are called discrete. So discrete mathematics is its own area of mathematics. If you get into any kind of computer programming ciphers, if you want to code your material, if you don't want people to know how much money is in your bank account and steal it, you need to have a code for it. That's discrete mathematics. Continuous is when we're looking at things like time. Time, no matter how small of a section of time you look at, there's always a smaller one. You can look at an hour, but they're smaller than an hour. You can look at a minute, but they're smaller than a minute. You can look at a second, but you can go smaller than a second. There's a millisecond, a nanosecond. You can keep getting smaller and smaller. And so it's a continuous time period. And so there's some things that are continuous and some things that are discrete. That would be like how many students there are. You can't have half a student. Well, you could, but that would be illegal. And so we'd have whole students, whole sheep, whole things, whole books. You can't buy half a book. And so some things are continuous, some things are discrete. So part of your work will be you'll be asked to sketch a graph of the situation and then decide if it's continuous or discrete. In this case, and on the helpful hints down here, we want to be very careful of our axes. What labels are we giving things? That is important. So a truck driver, they enter a street and drive at a constant speed. I'm going to start by just drawing an L. Those are the types of graphs that we're going to be looking at right now. We're just going to be looking at things in the first quadrant of our graph. So we've got speed and probably time, because when you drive, time passes. And so as time goes on, which if you've seen the movie Casablanca, you'll know as time goes on, we have some type of speed. The speed's either going up or it's going down. So the driver enters the street, drives at a constant speed. All right, so here I'm going to drive at a constant speed. They stop at a light. Now, You cannot go stop, right? I mean, that you can't go from moving to stopped instantaneously without any time passing. That would be, well, you would die. You have to slow down at a constant rate. You have to, when you apply the brakes, you don't immediately stop to zero. You can't go from 60 to 0 without dying. And so we have to show that we're constantly going down. So we've got a constant speed, and then we come to a stop. But we can't go straight down, because that would be impossible in physics. So we stop at the light, and then we're going to continue. And again, you can't go straight from 0 to 60 in 0 seconds. That's impossible. Physics says no. And so we have to gradually increase, even if it's a sharp increase, even if you have one of those Lamborghinis or Bugattis that you bought, you'd still have to gradually increase at some rate. And then they continue. So we have a graph that looks like this. Now, is that a discrete graph or a continuous graph? Since we've connected all the dots. Remember, a line is just a whole bunch of dots all put together. Since we've connected all the dots, we are going to have a continuous graph. We're going to have a continuous graph. Okay. Let's look at another example. We've got a graph. So again, I'm going to draw my first axis, or my first quadrant, excuse me. We've got my L. Small bookstore, sold between 5 and 8 books each day. Typically, when we have a graph, we're going to put time on the bottom. So we're going to have our days down here. Each day, so we've got, between 5 and 8 books for 7 days. We actually have some numbers in this one. So we got 1, 2, 3, 4, 5, 6, 7 days. 1, 3, 5, 7. There we go. We got all 7 days in there. And they sold somewhere between 5 and 8 books each day for 7 days. And we don't know exactly. We don't know exactly. And so we could have a range. We could say that, we go 1, 2, 3, 4, 5, 6, 7, 8. 3, 5. Okay, so I got my numbers on there. And they're somewhere in between each day. So somewhere between 5 and 8. And we don't know exactly, and so we can just plot some points. Let's say we have on day 1, 0.6. On day 2, maybe they sold 7. On day 3, maybe 8. On day 4, and you get the idea. So you don't actually have to be perfect on this because we don't know exactly. So we're giving a rough idea of what's going on with it. Now, can we connect the dots? Could you sell? Now, it looks like they're selling each day. They sold somewhere between 5 and 8 books each day. We're not looking at each half a day, at every hour. We're not looking at every hour. We're not looking at every minute, at every second. We're only looking at every day. So this would be a discrete graph because we're not going to connect those dots. Every day they count up. How many books did they sell? And at the end of the day, we get a number, but nothing in between. So this would be a discrete graph. Try this one on your own. Assume that you read it. Assume you tried it on your own. If you haven't, do that. We're going to sketch a graph. Okay, we're going to have an L. Jamie is taking an 8-week keyboarding class at the end of each week. Now that should be a clue right there. At the end of each week, which means that we're not counting every day. We're just counting every week. And it was 8 weeks. 1, 2, 3, 4, 5, 6, 7, 8. And so we've got our time on the x-axis here. So we've got our dates in there, our weeks in there. She takes a test to find the number of words that she can type per minute. So her words per minute. She can type per minute. She improves each week. Now, we don't know exactly how much she got, but we know that every week she's improving. And so we know that we don't really need to put any numbers on the y-axis. We could, but we have no idea what she can type. But we know it's going up. And so from week 1 to week 2 to week 3, 4, we don't know how much, maybe not quite as much that week, and maybe a little bit more this week. You don't have to be perfect as long as she's going up every single week, and we've got some kind of a pattern in an upward direction every single week, then we've done it. And this again, since we're only looking at the end of each week without looking at every day in between, this is going to be a discrete graph. Try one more. Last one. I'm going to assume that you paused it, you tried it on your own. So, draw my graph. Henry begins to drain a water tank by opening a valve. So the water is leaving the tank, which means that the amount of water that I have is going down. So I'm going to go ahead, since I've got, looks like my two different variables are water and seconds, so time. Seconds, our time is going to go on the x-axis, seconds. And we don't know exactly how many seconds, how long it takes, if it's a day or if it's 5 minutes or an hour. So we're not going to put any numbers. And we don't know how much water there is. But we do know that there is water and there is time. And we're going to look at how they relate to each other. So if he's draining the water from the tank, the water, I'm going to use blue, will be going down because he's draining the water. So the amount of water in the tank will be going down. Then he closes the first valve. Oh, excuse me. The first valve. Then he opens another valve. If you have two different valves that are going at the same time, you're draining a lot more water a lot more quickly. So he opens the other tank, it's going to start draining a lot faster. Then he closes the first valve. So he closes part of it off, which means it's going to slow down. He leaves the second valve open until the tank is empty. So he leaves that open, but it's not going to drain quite as quick. It's going to be a little bit slower of a drain, and eventually the water will go down to zero. Now, it won't be exact. Your graph shouldn't be exactly mine, unless you did it after me. But it should look something similar, where it's going at a steady pace here, a steeper rate there, and then another steady pace here that's a little bit shallower. So 3 parts to the problem. Okay, that's it. You've got some questions now on the form. Answer those, and then you can work on your assignment.